Welcome everyone. This seminar series, we run about once a month, and our idea is to bring together the tech community to discuss the development of technology, the role of technology in society. We'd like to get developers, researchers, and users, the academic community together, just to think about where technology is going and what maybe new ideas are coming out. These talks are hosted by the Masters of Science in Applied Computing program. This is a rather unique program in Canada and maybe almost one of a kind in the world. Our idea is to train graduate students to address the challenges faced in society, mainly in industry, but also in healthcare and other aspects of society, and really help them become the innovators of the future. Without further ado, I'd like to introduce our speaker. Zhen Gao is a founding engineer at COherent AI. He's also a alumni of the MSCC program, so we're very proud to have him here today. Steve manages a large team looking at language model optimization and productization. Prior to going to COherent, Steve worked extensively on perception models for self-driving cars at Uber, ATG, and he's well experienced in rendering engines. He's used in the computer graphics industry, and which is what he worked on before he switched his focus to AI, or to machine learning in AI. So Stephen, over to you.
Thank you, Professor Gupta and MSCC. Yeah, let me share my screen first. Hey everyone, I'm Zhen Gao. I work at COherent. Today I'm going to talk about bringing COhere's vision to life about the challenges of productionizing extremely large language models. So today I'm going to cover these topics. I'm going to talk a little bit about myself, my journey to get here, about COhere and our business, about the challenges specifically to training the models, the data collection and loading, inference on these models, safety of these models, as well as the organization to power these models. So a little bit about me. So I'm a founding engineer at COhere, first employee to join the company. At the beginning, I mostly worked with distributed training framework to develop the framework that enables us to train language models up to billions, even trillions of parameters. I also worked on efficient training research to make distributed training faster, more efficient, better device utilizations. I also trained a lot of massive models along the way and to productionize them to serve our products. So currently I manage a team to optimize model inference specifically and to do research on efficient model architectures to make the model more compact, less computation, while maintaining the same qualities. So a little bit about my journey to get here. I had my undergraduate degree in math at Duke University. I didn't know what to do, but I really just like science and technology in general, so I chose math. And then I got really interested into computer graphics, and I decided to pursue a master's degree at University of Pennsylvania. After that, I spent several years as a software engineer working on rendering engines and physics. I worked at Blizzard Entertainment, I worked at Crystal Dynamics. And then I decided to pivot to machine learning because I observed that it is the trend even in computer graphics. A lot of the new approaches are powered by machine learning models. And I think MSCC program really fits my need, the curriculum, as well as the timeline. And I was also part of the data science concentration. So as part of the program, I did my applied research at Uber ATG in Toronto. I worked mostly on computer vision, perception and prediction systems of the self-driving cars. So a little bit more about COhere. So we are a really fast-growing NLP startup headquartered in Toronto. We also have office in Palo Alto, California, and we're expanding worldwide to attract even more talent to our team. So we started about 2.5 years ago, and now we have about 80 employees. We are very well funded. We recently closed a 125 million Series B led by Tiger Global. So our mission is to build the most powerful NLP models and also make them safely accessible to everyone. Some of the products we offer right now are generated models. So with these models, you can provide a prompt or a context. The model will complete your context and continue to generate text. The second type of model is embedded models that given a piece of text or a collection will provide the representation or embeddings for these texts to do downstream tasks. We also have a little bit higher level API, which is classify, which use generated model to do few shot learning on the labels provided by the customers. In the future, we have even more ambitious goals. We want to build machines that really understand all type of human knowledge through the use of multimodal models to analyze not just text data, but also videos, images, and audios. So here is a quick demo of these products, so you will have a better idea of how they work. So here we have a console for the users to play around with our models to quickly prototype before they start using our API. Here is an example of the generated model. And in this case, we are providing a few shot example of correcting grammars. As you can see, the title has been corrected. And then we can also use this model to freely generate text given a context. Now we have the embedding models, which given various pieces of text, it will create representations, so-called embeddings for these texts. And in this console, it will also do a visualization. As you can see with these high quality embeddings, the questions that are similar to each other are clustered more closely. Lastly, we have the classify endpoint, which the user can provide a few small amount of labels, and our models can classify new inputs. Okay, so why do we think COhere can succeed in pursuing these ambitious goals? First, I think we have really good expertise in this area. So we have 3 co-founders. Aiden, who is our CEO, was a co-inventor of the transformer model. Nick, who was a co-author on the capsule network paper with Professor Hinton. And we also have Ivan, who was a founding engineer of a scalable serving platform before he joined. We also have a really diverse team of personal and professional backgrounds. We have a really high bar of hiring our engineers. We have top AI talents, both in industry as well as academia. We also have a multi-year partnership with Google on the use of a massive TPU cluster that will give us enough resource to train and productionize these giant models. So before we dive into these challenges, I want to give a quick recap of large language models. So nowadays, the dominant model are the transformer-based architectures. They have very elegant architecture. They generalize really well to different tasks. They are also very good at detecting the relationship within a long sequence. It's also been shown that these models scale really well with the increasing parameter counts. That's why you give a revenue of the emergence of these large language models, because they do not overfit as much as models like in computer vision. To train these models, we need a lot of data, but the good thing is we don't need that much labeled data. We can use unsupervised pre-training with all kinds of data sets collected from everywhere, including the web. And nowadays, it's not uncommon to see these models available or as a product of with parameters of billions or even trillions. So why is it so hard to productionize these large language models? So we stack more layers and we gather tons of compute. Is that enough? So we definitely need these two things, but we need a lot more than that. So first of all, on training these large models, the first obvious issue is these models are too big. For example, a 100 billion parameter model in a float 32-bit format will take 400 gigabytes of memory just to store it. And this memory requirement will quadruple during training because there is the model parameter, there is the gradients for each parameter, there is the optimizer states. For example, in the popular Atom optimizer, you have 2 moving averages per parameter. So realistically, we'll need about 1,600 gigabytes of memory to train a model. That's where distributed training comes into help. One of the most popular type is data parallelism, where each batch of data is broken and distributed into multiple devices. I think this is well known and people have a lot of experience with this, but itself alone is not enough to train these big models. Now we have model parallelism, which is really the most critical part of training these large models. So here is a diagram of a really naive model parallelism setup. You have 6 layers in your network and you partition it into 3 devices and you sequentially execute each device and relay the outputs from one to the next. But this leads to the second problem. It's too slow to train like this. First, the issue is due to model parallelism, it usually leads to much lower device utilization. As you can see from the previous graph, there is dependencies between devices. Devices have to wait for the output of other device. And a single step of training such big model could take hundreds of seconds. It's not rare to see the ETA of the completing one epoch will take 2 years or something in that range if there is not enough device or the framework is not optimized enough. So this leads to a lot of improvements about more efficient model parallelism. The first type is pipeline-based model parallelism. As you can see here, the way it works is instead of processing each batch at once, you will break it up into multiple smaller micro batches so that the later device can have less wait time. So with this setup, the idling of devices will be much reduced and the so-called bubble will shrink. The second type of model parallelism is tensor sharding based. So in this setup, the model is partitioned along horizontally instead of sequentially. And the advantage of this setup is there is less wait time, there's higher device utilizations, but it involves more communications between devices. It's also much harder to write the models with this setup. The third thing that's involved in making model parallelism more efficient is to optimize inter-device communications, because the data transfers between these devices is really one of the biggest bottlenecks, sometimes even more than the computation itself. So there's many ways to do this. First, one way is to find better ways on the cloud platform, given their technology, to have a higher bandwidth. Second is to compress the data needs to be transferred so that the overall speed can be improved. So now let's talk about training data. The first challenge is we need a lot of data to feed these giant models, usually corpus of multi-terabytes of size, which means we'll need to collect data from the internet. Sources like good sources like Wikipedia or books is not going to be enough, but the internet is full of low quality data. There is toxic content, racist content, terrorism, pornography. There is duplicated contents like news articles. People share news articles, different sites publish the same articles or blog posts. There is generic contents, which is contents that came out of templates. For example, the contact us page from an e-commerce site. So to really filter these low quality data, we need to perform filtrations at different levels. At the first level, we have model-based filtration. For example, this can be used to remove duplicated data or data that has been seen a lot by the model already. The way it works is, given a piece of text, we can ask the model, how likely is this whole sequence of tokens? If it's really likely, that means the model has seen this data a lot. Maybe it's a good idea to remove it from the dataset. We can also train a model on toxic content only and perform the same check with the text. If the likelihood is high, means this piece of text might be toxic content. Another way, which is based on algorithm, is locality sensitive hashing. This is a hash algorithm which is quite opposite of the normal hashing algorithm. This algorithm actually tries to maximize the collisions between inputs so that inputs that are more similar will end up in the same buckets. So this algorithm can be very effective in removing duplicated data. The third level is direct blocking of words and domains that we know are not safe or are not producing the level of content that we want. The second challenge of data is on the data loading side during training. So people rarely think about shuffling. When the data set is small, that's okay. But when you have terabytes of data, which is saved distributedly, it is quite hard to get a good shuffle. The second issue is robustness. So training job dies all the time, especially with training large language models, because with a bigger cluster, the chance of any device to fail is much higher. So we need much stronger tooling to deal with these problems. So for shuffling, it's gonna be much more complex than dataset.shuffle. We have to implement between files and within files shuffling, as these datasets are stored in many multiple files across the cloud. We sometimes also have to do pre-shuffling because we do not want the data loading to be the bottleneck during the training step. Data set example tracking can also help with the robustness problem. We want to track what examples we have trained on, which example within which serialized file that we were at each training step, so that whenever anything happens to the training job, we can restore it back to where it was. So next we have inference, meaning running the predictions of these models. So the first issue is too big. As you can see, these challenges look familiar. It's the same challenge as in training, but the problem itself is a little bit different and the solutions are a little bit different as well. So these models are too big to fit into any single accelerator like a GPU. And the storage for these models, especially when we have fine-tuned customers models, will multiply with each customers. One of the ways to deal with this problem is to implement compression algorithms. One of the most popular technique is quantization, which is to use a lower precision representation for the parameters. For example, models are usually stored in float 32-bit, but there is also 16-bit BF16 integer 8 format, which take much less space. So to incorporate these techniques, sometimes it's easy, but for the bigger model, usually it's much harder. There is going to be a lot of tuning involved to calibrate the range of parameters of activations. Sometimes these techniques also have to be implemented during training so that the model can adapt to this setup. Another very promising technique is matrix approximations, also known as low-rank reparameterization, which is essentially to approximate the giant weight matrices within these transformer models. Given a big matrix, it can be approximated as a product of two smaller matrices. So with this technique, we can greatly reduce the model size without sacrifice the quality. Lastly, we have distillation. Distillation has been a technique that has long been used in machine learning, but to adapt it to large language models is really hard. It's a very active research area. It's also very hard to do in terms of infrastructure. It is very hard to use a large teacher model, whether it's in online or offline setting. It's also extremely slow to do the teaching part as well. So the next challenge is it's too slow in inference. In inference, it's also more speed sensitive than training. When the user make a request, we want to deliver the result to them as fast as possible. And another thing that exacerbates this problem is the autoregressive nature of the generation type of models, where you have to generate one token, feed the token, attach the token back to the prompt, and then repeat this process until you reach the number of tokens you want to generate, which means if you want to generate 1,000 tokens, you have to run the forward pass 1,000 times, which is really slow. So some of the solution include sparse attention. Because attention is a quadratic operation in transformer, it's as you increase the sequence length, attention is usually the slowest part in the model. Sparse attention usually implements a different pattern instead of paying attention to all the previous tokens. So these techniques can really help to generate longer sequence. But in reality, implementing them is not easy. If there is not a proper kernels implemented in the hardware, it really could be slower than without using sparse attention. Another very popular and necessary technique is to use activation caching. Due to the autoregressive nature that I mentioned before, we can actually cache a lot of the intermediate activations for the tokens that we have already computed. This will greatly help the problems that we have to run the forward pass 1,000 times for 1,000 tokens. Lastly, we have a very general technique to improve the model speed. So each operations in any machine learning framework is implemented as a kernel down to the device level, for example, on a GPU. There is a kernel for matrix multiplication, there's a kernel for addition, for softmax. But whenever it's possible, whenever your model needs to do a sequence of operations, it's better to write a kernel that does everything in one operation. Because invoking new kernels has a really high overhead, as well as a high cost to transfer the data to the device. So next up, we have model safety, which is to make sure our model don't generate toxic content or bias, and also being used in a responsible way. The first challenge is it is really hard to evaluate model safety because sometimes it's really subjective in terms of what contents are toxic, what are biased. The second issue is there is a large categories of bad contents that we need to consider. So one of the promising thing is there's a lot more data sets emerging from academia that start to address this problem. So we have StereoSet and BOLD. These two data sets help measure the bias in the model, especially on gender, race, religion, and professions, on language models, and can provide a quantitative way to measure how safe is the models. We also have another technique, which is called universal adversarial triggers, which works by identifying a collection of prompts, which itself doesn't contain any toxic content. But when you provide the model with this input, it will generate toxic output. So using these triggers, we can measure our models in terms of how often they are susceptible to these triggers. the next challenge is irresponsible use from the customers. So there is websites who create malicious content, and they want to use our models to generate content. There is also accidents where the user didn't want to, but the model output undesired output. So we do have responsible use agreement with all of our customers to make sure that they use our model in a safe way. We also screen their businesses to make sure that they don't use our model for any illegal business or business that's harmful to the society. We also implemented on-the-fly model-based detection, which is based on the technique I talked about earlier, that tests the likelihood of every output with our models to detect whether it's toxic content or not. So lastly, we have challenges in the organization. So unlike traditional software development, we have to operate through very high uncertainty. This is mostly due to the extremely long life cycle of these large language models, from collecting the data to training to optimization to fine-tuning. It usually could take several weeks or several months. There's also many unknown unknowns, which means the problems that we cannot anticipate, from scaling the model, from how the hardware behaves when you reach certain scale. So one way to deal with this is really plan with a lot of cushion. If you feel this task can be done in 1 month, make it 3 months. Also, try to be prepared to act fast. When there is opportunity or cases where the projects actually finish on time, which is very rare, you want to make sure you always have the next project, the next model you want to train, so that we can always keep our compute busy. So the second challenge is there are a lot of competing goals to create the best language models. For example, the quality of the model and the speed of the model are competing goals. When we optimize or speed up the model through compression, it usually leads to some sort of drop in the model performance. So we really have to balance what's the speed versus quality that we want. Speed versus safety is also a competing goal. It's actually surprising, but it's true. Sometimes training with the toxic content can lead to increase in some benchmarks in evaluating the models, but that's not what we want. And to deal with these problems, the organization really needs to have very strong trust between all the teams who's responsible for different aspects of the models. This will allow you to, for some team to make sacrifice or to raise problems without making others feel hurt. Lastly, we always ask the customers, because in the end, we want to build a business that provides value and to solve a technical challenge that our customers have. That's all. Thank you so much. I think now I can start to answer some questions.
Yeah, thank you, Stephen, for that very interesting talk. Just remind everybody, if you have questions, please post them in the Q&A, and Stephen is going to start answering questions for us. So Stephen, go ahead.
First question, in the tensor sharding approach, how will we debug a straggler? For example, we notice one device is very slow or the bottleneck. So in this setting, especially when we have a cluster, we have a system to monitor the status of each device, whether they're processing the inputs or they're idling, and this will help us detect any issues. Is zero parallelism developed by DeepSpeed enough to train big models in the industry? Or did you have to implement other techniques in order to parallelize? So zero, I think, to people who are not familiar, zero is a technique that reduces the memory usage of optimizers, which is really important, but itself is not enough. I think I mentioned several other techniques that we use in combination. You were working in computer vision at Uber. What made you switch to NLP? Yeah, I haven't thought about, I didn't think about NLP while I was at Uber, but I had a chance to talk to our co-founders at COhere. And I think it's really their vision on NLP, on the type of challenges it can solve, that convinced me that this is the future. Can you talk more in depth about tensor sharding parallelism in model parallelism? I'm trying to understand how it works. Thanks. Yeah, tensor sharding parallelism is really hard. I suggest people who are interested to do some reading. For example, Mesh TensorFlow is a good framework, as well as they also publish a paper. It's a good starting point to understand. Seems like what Cohere is doing and with its product is very similar to OpenAI. So what differentiates Cohere? Yeah, so that's a really good question, and I got asked this a lot. So OpenAI is a great organization, and they have done some really impressive research pushing the field forward, and we really respect that. And we actually also start to collaborate with them on some model safety standards. But in terms of differentiators, I think OpenAI, they are a research lab and we are a product company. So our DNAs are very different. Lastly, I think this space, this NLP space will be very big. There are gonna be multiple players and each player can all be successful playing a slightly different role. How would you say your experience in the MSCC program has helped you with your career goals? I think it helped a lot. It was very tough to transition from a different field into machine learning. But through the program, first of all, the coursework, I really did learn a lot. And the second thing is the applied research project, which is 8 months long, where you really got a lot of hands-on experience. Yeah, I think it's a combination of this two. What's the main use case in the market, your customers, for Cohere's APIs? We have a pretty wide range of different customers of different industry. One of the popular one is to generate content for blogs, for marketing materials. We also have chatbot companies who want to categorize the support tickets or chat logs. We also have social media companies who want to use our model to curate content. Yeah, there is a lot of different applications. Curious, how do you identify those universal adversarial triggers for large language models? Yeah, this is a really good question. I am not an expert in the safety part of our model. So yeah, I cannot answer the detail, but there is a paper on universal adversarial triggers for NLP. So I think that will, yeah, help you. Can you discuss a bit more about attention sparsity for inference, its lossiness, and perhaps point us to some papers? So there is a lot of different type of sparse attentions. I think to get started, the most basic one is the local attention. I think you can just search this local attention for transformers. You can find any papers. What's the difference between research intern interviews and software engineer intern interviews? Yeah, we don't have this differentiation. So yeah, I cannot answer that. When working at a startup ML company, what factors differentiate you from the other startups? It seems that it will be difficult to create something novel since most of the work is from the latest published research. It is true. I think for any ML startup, the first thing is you have to have the talent. Have the talent to not just to push on the research side, but to implement systems. And the second thing I think is to have great partnerships with hardware providers, with open resource organizations, so that you can get a lot more progress and help through the use of their technologies. How does COhere AI deal with distribution shift for language models? Yeah, that's a good question. Since we collect data from web, and given our world is changing every day, the news, the contents we collected will be irrelevant in several months. And that's why, yeah, we have a continuous progress system to collect data, and we refresh our models on latest data so that the model knows what's happening in the world. What do you think about other players other than OpenAI are doing in the space, like Hugging Face, who is open source? I think Hugging Face is great. That really allows many small developers to have access to good quality models. But I think for us, we want to be a complete solution for the customers, as well as provide models that's unplausible for many of the customers, for models of tens or hundreds of billions parameters. Open source library cannot fix that issue. The customers cannot run a whole infrastructure on these models, and yeah. How do you scale up and down clusters that host large language models? So I guess this really depends on whether this is in training or in inference. So in training, we have dedicated clusters because it's much more cost effective, and we have a lot of work that can occupy this cluster. But for inference, we do have a load balancing server that will scale up the devices according to the requests. What's a good starting point to find supervisors for projects that are at the intersection of ML and other industries, such as medicines for MSCC program. I think there's various courses in the MSCC program. For example, I have taken the machine learning for health, which was great. I had a publication came out of that. I think, yeah, finding the course that that is specialized in the field that you want is probably the best way. Can you tell us more details about the infrastructure you use for training and the inference, and some challenges you've faced dealing with such large models and data? So for training, we have the massive TPU cluster from Google. So the one thing is really hard about using these clusters is writing all the model parallelism and make it efficient to training, which is really challenging. And then for inference, we use GPUs. The GPUs is more optimized for latency and speed.
Maybe we'll leave it there. I know there's lots of questions, but I really appreciate you spending so much time going through the questions with us. And you can see lots of students are very interested in what you're doing. And I'm sure some of our students will want to talk to you in the coming years. So thanks again for that really interesting talk. Learned a lot. And I want to thank everybody who came today to hear Stephen. Please visit the MSCAC website. You can see all our talks. We have other events that we'll be hosting. Welcome all of you to come out and visit with us. Thanks again, Stephen, for your time, and thanks everybody for coming out. Have a good evening.